Sorry. May I ask if you mind if we record your talk?
Of course, that's fine.
Okay, thanks. Jay, please start recording. Adrian, please start.
Thank you. Yes, as Zoe said, my name's Adrian Jackson. I'm from EPCC at the University of Edinburgh, and we're also one of the partners in the HPC Wind Energy Project, where we are bringing in expertise in high performance computing and code optimization and things like these. And today I'm going to talk about work we're doing to look at improving the I/O, so improving the performance of reading and writing data from applications. And actually this builds on work we've done in the past in another European funded project called NextGen I/O, which finished last year, which was looking at providing sort of new hardware for doing optimized I/O for applications. And that's where this non-volatile memory part of this comes from. So okay, so the work we're doing in this part of the wind energy project, the HPC Wind Energy Project, is looking at how we can improve I/O performance for applications, actually for two reasons. One is that I/O can often be a bottleneck for a lot of applications, particularly engineering applications, but also we have a interest in improving I/O performance so applications can write out more data, because we think there are some scenarios where you may get more scientific insights or you may get benefits by allowing applications to produce more data and then go through and process it afterwards or analyze it afterwards. So we're looking to optimize the I/O performance, both to improve the application performance, but maybe also to improve the amount of data that applications can routinely save, because it may bring some more scientific insights that way. Now, as I said, this work we're doing here builds a little bit on previous European projects where we were looking at bringing in this persistent or non-volatile memory into high-performance computing systems to optimize the movement of data in and out of a processor. And so, nowadays, memory systems for computers are getting more complicated because there are more options available. In the past, we had caches on the processor to improve processing performance and bridge the gap between the speed of a processor and the speed of memory. And then we had storage. We had disks or tape storage further out, which would keep your data long term, but is slow. And you need the volatile memory, the normal memory in the processor, the DRAM, to bridge the gap between the storage and the processor. But nowadays we're seeing an increase in the complexity of memory available for building systems from. We now have routinely high bandwidth memory available on various processors. So there's a new processor from the Japanese, Fujitsu and Riken, which is the thing that powers the fastest computer in the world, Fugaku, this A64FX processor. It has high bandwidth memory directly on the processor, and it has no external sort of DRAM or memory, and that gives them much better performance for some applications. GPUs have been routinely using high bandwidth memory directly on the processor over the past few years, and so we see another level of fast memory being available between processor caches and main memory. But we're also seeing a new generation of memory hardware, non-volatile memory, or what we end up calling byte-addressable persistent memory. It's the same thing, which is slower than main memory, but much faster than storage you had in the past, and much faster than spinning disks storing your data, much faster than tape drives, much faster even than SSDs. And actually that moves, looks like it can help us move our computer architectures forwards to a place where maybe we simplify the memory hierarchy again, and we have caches on the processor, we have high bandwidth memory on the processor, and then we have some non-volatile memory sitting in the node or sitting somewhere else to do our long-term storage, and we can get rid of disks, and we can get rid of SSDs, and we can get rid of tape drives. Maybe. Now, of course, there's always trade-off with these things. So if we have a look at the the different characteristics of these kinds of memory, the high bandwidth on processor memory is very fast, but it's costly to implement. It's costly in terms of energy, and the latency is actually quite high on them. Normal main memory, which we've been using, normal DRAM, which we've been using for processors for the past 30 years, is fine, but it's quite slow compared to processors, and it's quite costly in terms of energy and maintaining data on the chips. The byte addressable persistent memory, or the non-volatile memory, is much higher capacity than any of those other forms of memory, so we can get much more data on there. And it's potentially much lower energy as well, because it's non-volatile. That means once you've put the data on it, you don't have to give it any power to keep the data there. So you put the data onto it, and then if you're not using that data, then it's potentially not costing you any energy to store it there. Just like if you've got a spinning disk and you're not reading from it and the disk shuts down, it's not using you any memory. Now, we've had non-volatile memory for a long time. You'll all have SD cards that go in your phones or your cameras, which store data on them. That's non-volatile memory. It's been around for a long time. What is new about this new forms of non-volatile memory, which we're using here in this work and in the previous project, is its performance has now come on enough that it's close enough to memory that you can think about using it in for performance critical bits of your application. And two, it's sort of because its performance has come on, it's now possible to use it in a different way than we used it before. Particularly, the memory I'm talking about at the moment is what we call Intel's Optane DC persistent memory. And what's interesting about it is it comes as a memory module which you can plug directly into the computer rather than something that looks like a hard disk, rather than sitting on a PCI Express bus or a SATA interface or something like that. Now, you don't care about all these kind of things, but the nice thing about that is it allows you to address memory on it in a much more normal manner for applications. So you can get individual bytes of data from it rather than having to go and get very large chunks of data. Again, this starts to get into details and things that you generally don't have to consider when you're writing an application. But the way we generally read and write data to disks, to external file systems, is what we call asynchronous block I/O, where it's optimized to send large chunks of data or read large chunks of data from the disk, and performs very poorly if you try and access it in a, I only want a byte, I only want 5 bytes, I only want 10 bytes of data, and then I'll get some more data later, as you would normally access data in your volatile memory in your caches. So the really nice thing about this form factor of memory and this new non-volatile memory is we can access it as if it's memory, as if it's random access memory with good performance, but the data stays there once we've written it there, so we don't have to worry about putting energy into it to keep the data there like in normal memory, and we can turn the computer off and turn it back on, and we get our data back out again. Of course, there's all sorts of complexities wrapped up in there, things like security and error correcting and all those kind of things. But you assume that all that works, and we have this potential for very large on-node storage at much faster speeds than we've had for disk before, and in a manner where we can access individual bits of data quite quickly. And so that's what we're looking to say, can we use this in our applications, in our CFD applications, specifically for this project, to improve performance and improve functionality going forward. The other thing that's also worth bearing in mind for this new kind of memory is it's asymmetric in terms of its performance. So the reads are much quicker than the writes. And that's just because making sure the data stays there, making sure the data is persistent takes more energy and therefore longer time when you're writing it than when you're reading it. When you're reading it, you can just read it. When you're writing it, you have to take a bit of time to write it. And that's just a function of this type of memory, the way the physics of a memory work. But that means, of course, when we're going to try and exploit this for our applications, we have to be a little bit careful about that, because if we put data there that requires lots of small writes, then that may give us worse performance than if we put in data there which requires lots of small reads. Now, this memory is slightly complex in the sense that you can use it in different ways. There is a way to use it just to make you have much more larger amounts of memory for your application. So you don't use the persistence, you don't treat it as storage, you just treat it as a very large memory space. Your application never sees that it's special memory, it just sees it's got a very large, it's slower memory space to use. And that can be useful for some applications. If you've got a big code that doesn't parallelize well, but you need lots of memory to fit it into to run a particular simulation, then this sort of way of using this memory, what Intel call Intel memory mode, or we call two-level memory, is one way of doing that. Now, I'm not going to talk about that in this presentation because it doesn't really use the nice features of this memory, but it is one way of using this memory as well. So why are we interested in this at all? Well, it's because, as I said, we get really good performance in our compute nodes for this storage if we can exploit this kind of memory efficiently. So here is some benchmarks from a system we have in Edinburgh where we have 34 compute nodes, each with some of this memory inside it. And then we're running an I/O benchmark to see how fast we can read and write data to that. And here, with minimal effort, well, in fact, hardly any code changes at all, we can take an application that benchmarks I/O systems, application called IOR, run it, and we can scale across the 34 nodes up to about 1.8 terabytes a second of data we can read, and we can write about 300 gigabytes a second of data from the 34 nodes. Now, here you can see this asymmetry I said between the reading and writing of data. See, the reading of data is somewhere between 5 and 10 times quicker, usually about 5 times quicker than the writing of data. But even so, this is very good performance. I mean, sitting in isolation, it's hard, I imagine, to tell whether this is good performance or not. But if I can put it in context, our slightly old now large Cray system we have in Edinburgh called Archer, which is the current UK national HPC service for science and engineering, it's been replaced at the moment, but it has a peak bandwidth on its I/O system for the whole thing, which is 118,000 cores of 20 gigabytes a second. Now, as I say, it's old now. When the new Archer 2 comes in, we'll have a much faster I/O system than that. But you can see here we're already at orders of magnitude faster than that file system on Archer by using this, and we're only up to 34 nodes here. We're only up to about 1,500 cores on this system. So this memory technology, we can see, can potentially give us a really nice performance if we have applications which want to read and write lots of data. And that's a big if, of course. So the other nice thing about it is because the way it's structured is you put the storage inside each compute node in these memory modules that you plug in, we can also get rid of sort of contention-based issues on the I/O. So here on my left is a graph of a Lustre file system, which has got a number of different applications running, and the big yellow bit is some application has kicked off and is writing a large amount of data. And now, because that file system is shared between all the other jobs that are using, they'll see a slowdown in what they're doing when this application is running. And on the right-hand side, this probably barely legible graph to you. Apologies for that. But on the right-hand side, I've got a graph here of some I/O monitoring we did on and benchmarking and monitoring we did on an application where we ran the same application every day, 10 times every day for a month to see what performance was. And if we look at the I/O parts of it, we can see most of the time the I/O for this bit of the application is taken under 5 seconds, somewhere like 2 or 3 seconds. But depending on what else is going on in the system, we have points where that same bit of functionality, reading or writing the same amount of data, can take 10 times longer, can take over 30 seconds. And that's, just demonstrating that because the I/O systems are shared, on normal HPC systems, you can get this interference between your job and somebody else's job. And putting the storage inside the compute nodes gets away from that issue because we have our own dedicated I/O hardware for each job. Now, that sounds nice. Of course, it just doesn't come without challenges, because once you start putting the storage inside the compute nodes, you need to be able to move data in and out, and make sure any data you write is available to you after the job runs, and work out what happens if jobs crashes, and make sure none of your data is left around for other jobs to read when they come on. So there's all sorts of system wear and usage things that we need to address there. But potentially we have really nice performance from that. So as I said, we're building here on work done under a system called a project called Next-Gen IO, where we built this system in Edinburgh, and we have these 34 nodes, each with 3 terabytes of this non-volatile memory in it, and 48 cores per node. And that lets us play around with this and run applications on there and see how they could exploit this memory, and what benefits they would get if they did exploit this memory. And so the other aspect of it, which is also interesting, is because it's set up as memory rather than storage, you can actually read and write small amounts of data very efficiently. So applications reading and writing to normal file systems only perform well if you're starting to read and write in large chunks, say, a megabyte at a time or 2 megabytes at a time. If you read and write in small chunks, the performance drops off quite significantly. And that means that we now have a way of moving with this memory into a model where we can still get the same performance, still get that sort of 1.8 terabytes a second, even though we're reading and writing at smaller amounts of granularity. Now, it's a little bit complicated what's going on here, but we have the graphs at the bottom here are doing I/O in 2 different ways. One is called FSDAX, which is just reading and writing the data as if it was a file. So it's just using the normal file system interfaces. And the other is PMDK, which is the Persistent Memory Development Kit, which is the programming library and interface to let you use this memory this new storage in a memory-like way. And we can see on the left-hand side, I've just rerun that benchmark I showed you before, where we've got about 1.8 terabytes of read bandwidth. And if I run it with a file system, FSDAX, or if I run it with a PMDK, I get the same performance between both, right? On the left-hand side, I don't see any benefits from using this special, functionality where I can read and write small amounts of data very efficiently. But that's because this bandwidth benchmark is set up for file systems. So it's set up to read and write data in large chunks to get best performance. If I modify that in the graph on the right-hand side, here now, instead of reading and writing data in 16 megabyte chunks, which we're doing on the left, in the right-hand side, we're now doing it in 256 byte chunks, which equates to a cache line, which is really the smallest amount of data I can work on the processor. And apologies, the colors have changed, but we can see here that the read and write for the PMDK, the green and the orange, are the left 2 bars on each data point, are now close to 2 orders of magnitude faster than the read and the write from the FSDAX, which are the right 2 bars. And we haven't changed the functionality here. We haven't changed anything but the granularity of our data accesses. And we can just see that that memory interface system lets us read and write that data in smaller chunks at the same performance as if we were reading and writing it in large chunks. Whereas if we have to go through a normal file interface, we don't get that performance at all. And so that's what's actually, to me, really the most interesting thing about this persistent memory is it lets us change our applications. So instead of doing bulk I/O operations, saving up our data, writing it all out at the end, or reading in all the data for a simulation at the beginning and then going off to do the work, we can move to decoupling the I/O from that bulk nature into something much more small and often. And we could only, for a lot of applications, that may mean reading in only the amount of data you need to process at this time step or at this part of the simulation, and not everything. And that means we can reduce the amount of resident set data we need and use small amounts of memory or fit into smaller numbers of nodes and still maintain the performance we had before. And this is, the same benchmarking, but just looking at varying block sizes from 128 bytes up to 16 megabytes. The two graphs on the left-hand side of a file system, the FS-DAXWE, and the two graphs on the right-hand side of this PMDK, using it in memory. And all they're showing you really is that we can get the best performance we get with small amounts of data, with anything between 128 bytes and 32 kilobytes on the right-hand side. Whereas on the left-hand side, we need to get up to 256 kilobytes, 512 kilobytes, really, blocks, data movement chunks before we get any good performance. And that's exactly the same thing. So what does this actually look like in practice? How easy is it to use this memory? How hard is it to use this memory? Well, effectively, it's pretty straightforward, at least if you're running C and C++ codes, because the current PMDK library is just set up to treat this as what we call memory mapped I/O. So effectively, you can just pretend that the storage is memory as long as you set it up in the right way. And the Fortran is perfectly possible to use as well, but we just need to do a little bit of interfacing between Fortran and the C code, which does the actual memory mapping calls. So we just need a Fortran to C ISO interface, and that's perfectly fine. But so just to give you some examples, a couple of the test applications we use for teaching, excuse me, in Edinburgh. This is an image sharpening example where it's a 2D stencil code effectively, but for us to move from using normal memory, so it's not about storage here at all, it's just about memory, using normal memory to using this non-volatile memory, all we have to do is replace this top line, this malloc at the top, with a PMEM map file at the bottom. And that changes where the memory is allocated. And then after that, we can just use the data exactly as we used before. We just have to change that one malloc, or that one allocate. And then we can just use the data as we used before. Effectively, we also have to replace the free or delete functions at the end. But I haven't shown that here. And in this case, I could actually replace the volatile memory, our normal DRAM, which is faster, with our non-volatile memory. And because I'm only replacing read-only data here, actually, I get exactly the same performance as before, but I get access to much larger amounts of memory. So on these systems, I have 192 gigabytes of DRAM, but I have 3 terabytes of non-volatile memory. And so I could run a simulation here of up to 3 terabytes rather than 192 gigabytes and get very similar performance as if I was using the DRAM. Now, this is a toy application and it's not doing anything particularly clever in there. We also use a 2D CFD streaming function kernel for some of our teaching here as well. So again, another quite simple kernel, but we could look at replacing this sort of Jacobi kernel update and if we take some of that and put it in the non-volatile memory, what kind of performance impact do we have here? And so again, we can do that kind of thing here by setting up allocating my memory here and then doing some pointer swapping. And so I can take one of these arrays, one of these either psi or sin u, and put it into a non-volatile memory, cut my DRAM usage in half, and see what kind of performance impact that has there. And so you can see down the bottom here that it does make the code go slower because this non-volatile memory isn't quite as fast as volatile memory. But we don't get a huge performance impact. You've got something like a 20% performance impact here. And in this persistent mode here, we're actually, saving that data into the non-volatile memory, so it's stored long term as well. So we could do our simulations there and keep the data there if we want to. But of course, that's all just playing around to demonstrate how the actual program of it's easy and the performance isn't terrible. What does it look like when we look at actual applications? Well, one of the things we did in the Next-Gen I/O project was look at OpenFOAM and what performance we get with OpenFOAM. And particularly, actually, we're interested there in not just the solver, but the whole process, the whole workflow from meshing to solving. And then after that, to visualization, these kind of things. And so we took in this instance, it was an aeroplane simulation, pipistrel aeroplane simulation, reasonably big. We needed 16 to 20 nodes to run it for what we were doing here sensibly. And then we look at running it on Lustre, which is our external file system, to running it on this byte addressable persistent memory or this non-volatile memory in the node where we're not using the Lustre file at all. The decomposition and the solver are two different steps, so we have to do the decomposition first and then the solver. And so if we do the decomposition on this non-volatile memory, we then have to move that data that's produced potentially onto new nodes when the job actually runs, and that's what the data staging part is. And then we look at what impact that has on the solver. So we're only running the solver for a few iterations here. In reality, you'd run the solver for 100 times longer to do a sensible simulation. But we can see that here, even for our 16 node example where we're doing minimal I/O, we get a reasonable performance improvement here, where we're 46% faster, where we're not doing loads and loads of I/O, but we're doing some I/O here. In our 20 node example on the right-hand side, actually we cranked our I/O up, so we're writing out the data every time step. So much more I/O than you would generally get away with on a normal HPC system, just to see what happens. And the nice thing is there that going from the 16 nodes to 20 nodes and cranking up the I/O, we really don't see any performance difference between the I/O at 16 nodes and the I/O at 20 nodes on the byte addressable persistent memory. It goes from 66 to 78 seconds. And we've gone from writing out every 100 time steps to writing out every 1 time step. And it's really not made that much of a difference. Whereas on the Lustre, the normal file system, it's now going 10 times slower. Okay, so we can see here, this lets us do that optimization of producing much more data, but not impacting our performance. And then we have some costs associated with, moving the data around after the job is finished, of course. But that in that project, that was all handled by systemware for you. Now we started looking at things in HPC wind energy as well. So one of Zuri's cores, N3D with Centex, we were looking at performance there. And so the small test case that we have for that can use up to 72 processes, and that produces about 1 million files, or about 4.5 terabytes when it's running. But we have a larger test case, which runs up to about 512 processes, and that produces 6.4 million files, or about 30 terabytes. And so these kind of volumes of data are quite hard to handle on the Lustre file systems we have running here. But they're important in the application because they're a way of saving data from one phase of the application, so from the forward phase, and then reading that data back in again in the adjoint phase. And because you can see even in the small test case, it needs 4.5 terabytes of data, it would be very hard to fit that in memory and keep it in memory for the application to use without writing it to disk. On a system like this, where we've got 192 gigabytes of main memory, we'd have to go up to a large number of nodes to fit this in. We'd have to go up to 20, 30 nodes to fit this in memory. Whereas we only need 72 processes to run this, so we only need 2 or 3 nodes on this system to run it. Likewise, in the 512 test case, we'd need to go up to hundreds of nodes to fit this in DRAM, but we can write this out to the memory. So what we've done is taken that write phase and write it to the persistent memory on the nodes instead of an external Lustre file system. And you can see in this small test case, it saves about 10% of the runtime. Okay, so it's not huge, it's not massive, because not all the code is involved in this reading and writing of data, but it's significant enough to be worth doing. But when we go up to the larger test case, we can save much more, because the bigger a test case, the more we're using the file system, the more expensive it becomes, and the more that becomes a bottleneck. And now we can sort of see, 50%, 60% of the runtime might be saved by doing this kind of test. And the nice thing about these test cases is just temporary data. So it's only writing the data to read in a later part of the solver, and then it can be deleted. We don't need to pull it back off the nodes again. It's just using this as temporary small storage. So that's the first phase. We can see the benefit there. Now we're going to have to look at seeing, can we change the code to, instead of using files, write it as memory and see what performance benefits that has there. Anyway, I know I'm running over time here. There's some complexity in terms of how you use this in terms of uniform access and getting the right performance, but it's easily overcome if with a bit of nasty code like this you have to put in there. One of the places it's really interesting, as I said before, is in workflows. So where you have a job which does multiple stages and passing the data between those stages, if you don't have to then do that through the file system, you can do it through this memory. You can really cut down the amount of time and the amount of energy required to move data in and out of these systems. And maybe in the future, get rid of that external file system altogether. But of course, that requires a fair bit of support in the system, which isn't there yet, to make sure that your user's data is in the right place at the right time and protected and all those kind of things. So, we've only just started, we've only started recently in anger doing some of this work on the HPC wind energy codes for the I/O side of it, but we see some real benefits there. And this kind of in-node storage, I think, does have a place to play in future HPC architectures, but we need to do some work with the codes first to see the easiest way to use it and the most efficient way to use it, and sort of demonstrate that to people before it's going to become widespread and available going forward. But I think there's, in that workflow stage or in that optimizing I/O stage, there's some real benefits there to using this hardware. And so that's where I want to finish. The only other thing I'd say is if anybody's interested in using this kind of hardware for their applications as well, please do come and talk to us, because we have this system and we can get people access to it to play around with as well if they think it would be interesting and useful for their codes. Yeah, so if there's any questions, I'm happy to take those, but I realize I've overrun as well, so I'm happy to take those questions offline if that's easier.